Hi, this is the lecture 7, which is actually second lecture in the module on deterioration of cementitious systems. In lecture 6, we covered introduction for the durable concrete systems and then also sulphate attack and acid attack. In this particular lecture, we will cover frost attack and freeze-thaw attack and also alkali-silica reaction in concrete systems. Now, to talk about the frost attack, or first thing is where that will actually happen, and we have a lot of region in our country where the temperature could be less than 4 degrees Celsius or ambient temperature. So, we define that as cold climate, and as you see in this picture, you can the map you can see that this region, all this blue region are regions where cold climate is experienced. Even in other parts of the country you can see some hill stations etc., where the temperature could be very low or can be defined as cold climate. And if you really talk about the northern border, you even have places where the temperature during the night could be even minus 35 degree or even less than that. And eventually what happens is for construction purpose we get only a few months per year, like 2 to 3 months per year, to actually work comfortably in an outdoor environment. And it is not only temperature, we also have to consider the wind chill factor. So, these all, and also you might have diurnal variations, that is daily variation of temperature. So, all these have to be considered when we talk about good quality concreting, and it is not very easy to construct during that climate, cold climate, because we ourselves won't feel much comfortable in that climate. And but we have definitely a need for good quality concreting in places like what you see on the screen, especially on the border regions, very high altitude region with very difficult to reach terrains. How do we do good concreting in such cases, which is very important for our defense systems, because we might have bunkers and other facilities which need to be in good quality. So, in this lecture we will kind of focus on how to do good concreting in such harsh environment and very difficult to reach environment also. This is a you can see on this picture completely snow capped region, and toward the center of that picture you see a black circle, and there is actually a home which is being built. And this example I just put it here because that particular building took about 8 years to construct because of the harsh weather conditions. So, this is very important, and important to consider good quality good construction practices, so that we can reduce the duration of this construction from 8 years to maybe couple of years. So, we have to really think, and also another point is even if we take 8 years to construct, how long that particular facility will last, can it be durable. So, all that also have to be considered when we talk about because this is first of all in these conditions it is very difficult to construct. So, our objective should be when we do it, it should be of good quality, so that we do not have to go on and repair also in these difficult terrains and climatic conditions, harsh climatic conditions. Now, this shows a little bit, shows pictures of transportation systems, or you have a bridge and an asphalt road which is also heavily damaged because of moisture attack, and also the poor quality asphalt, and then which leads to severe damage when vehicles run over them. And then on the right side you have an image showing a wheel with chains, metallic chains, which are sometimes necessary to ride these vehicles in a very harsh climate. So, what these chains do is they, as the wheel is rolled, the chain kind of breaks the ice and then make it easy for driving on ice capped pavements. And the picture on the bottom left, you can see toward the center of that picture, there is actually a maybe we could say a highway in that region, and all these have to be of good quality. And how do we really achieve that good quality and long lasting? Again, let me emphasize the point, construction itself is very difficult in these locations, and so if you do not pay attention for durability, the constructed facilities may not really last long. So, we must ensure that the quality of construction is also very high, and once constructed it should last for as long as possible. And this picture shows that in most cases the construction is not good. It is not in this day at which this picture was taken, probably was a relatively sunny and nice day, but this particular region experiences very cold climate, and probably the construction was not done with good materials and practices. Of course, there could be other reasons also, non-technical reasons also, but at the end the concrete was not treated well, and it took 23 years to construct because of various other reasons also, but only 1 year to get damage. It is irony there. Now, what are the reasons? Mainly harsh climatic conditions and poor concreting materials and practices. So, this is not something that is acceptable, especially when we talk about very difficult to reach terrains and very harsh climatic conditions. So, objective of the concreting in cold weather should be that you do it and do it in a proper way, so that you do not have to go back and then the structure does not really experience a lot of repair, but we are having a lot of structures where repair is needed. Let us look at in this remaining slides. I am going to talk about what are the various mechanisms by which concrete in cold weather conditions, what are the difficulties associated with concreting in cold weather conditions. Now, if you say in fresh state or early state of concreting, there are 3 parameters which are important to consider. You have to have the concrete should set very fast or as early as possible, and the early age compressive strength also has to reach a significant a reasonable level. Typically we say 3.5 MPa, and then thermal crack resistance is also very important. So, all these can get affected when the temperature is very cold, and in hardened state also compressive strength may not reach if the temperature is very cold and if concreting is not done with adequate measures. And other things which can happen in the long term is pop-outs, decracking, internal cracking, scaling, etc. So, we will cover all these in the remaining slides which are upcoming. What are these different mechanisms? Now, first thing when we talk about cold weather or frost attack is there is an ice formation which happens in concrete. So, where is this water which is used for mixing the concrete? If the temperature is very low, it will become ice, and as we know, ice formation means an increase in the volume, which significantly 9% increase in the volume, which leads to significant expansive stresses in the concrete. So, the first picture shows that 9% increase, and the second picture shows a system where there is not enough space available inside the concrete, which will eventually lead to cracking because of this ice formation. And the third picture is basically showing how can we control this scenario of cracking by the black circles which you see there in the third picture is basically the air voids which are introduced, or entrained air voids, not entrapped, but entrained air voids. In other words, its air is added as an ingredient in concrete, and we typically use about 5 to 6% of air by using some chemical admixtures, air entraining admixtures. So, the idea is these air voids will help to provide space for this ice formation without inducing any expansive stresses. So, this is the main idea of how to handle cold weather concreting. So, let us see in particular some more details of in this frost attack, which happens mainly at early ages. So, these ice lenses are formed, or ice is formed at the surface of the concrete first, and then as it expands, like you see on the picture on the top right, you will see that this wedge like ice is formed, and as it expands it pushes into the interior concrete, and which leading to cracking. Essentially they end up in fracturing the concrete or leading to cracking, and in fresh state itself this can happen, and in other also in fresh state when this happens, the mixing water is actually consumed, or is used, it becomes the ice, and so sufficient water is probably sometimes not available for the hydration reaction also. And what it ends up in is you have an irreparable loss of strength, which is very, very important, because we if you do not get that strength, then what it means is irreparable loss. What it means is you cannot really gain it at a later stage, and the strength can decrease by about 50% if the concrete is frozen within first few hours of placement or before it attains 3.5 MPa strength. This 3.5 MPa strength requirement is given in most of the codes. So, in cold weather concreting, when we talk about, we have to first ensure that the concrete gets 3.5 MPa, then you go for protecting that concrete further by ensuring adequate moisture and temperature. So, we will cover that later, but remember this number 3.5 MPa, it is very important. Now, time of the onset of frost damage is also most important. That means, if the frost damage or that is happening after 3.5 MPa strength is attained, then we can still manage to get sufficient strength later. Okay, now let us look at delay in the early strength gain and reduction in the later age strength. So, this graph, the top graph, this one, it shows strength gain of about 40 MPa in 28 days, which is this line here. You get about 40 MPa, but the same concrete, when the ambient temperature is minus 4 degrees Celsius, it gains only about 10 MPa strength in 28 days. So, significant reduction in the strength. And another important thing to notice here is, after that, when the temperature is maintained at about 23 degrees Celsius, still it is not able to reach the strength which the other concrete which was exposed to 23 degrees Celsius from the very beginning. So, there is a significant reduction in the strength, which I am going to call as irreparable damage. So, that strength you cannot gain, because after this about 90 days you can see that it is almost, the curve is almost flat. So, there is no significant strength gain after that. So, you have an irreparable damage when we are talking about very low temperature. So, this is something very important, and let us see in the future slides how to take care of these issues when you talk about cold climate. Now, ice formation in early stages can, in the previous slide we were talking about strength, now it can also affect durability of concrete. How it affects durability is, if you look in the graph here, this is the solid curve is the amount of ice formation, and the dash curve is the permeability of indicates the permeability of the cement paste, or let us say concrete. So, you can see that the permeability decreases as more and more ice is formed, and what in reality what will happen is, later, once the temperature, once this mechanism is over, after some time, if there is an increase in temperature, then the ice which is contained within the concrete will melt, become water, and that water might also evaporate at a later time. Anyway, you will end up in having more pores or voids, which leads to higher permeability, and definitely you will have reduced durability in such cases. So, this frost attack is also very important to consider, when not only for strength, but also for durability. Now, other effect is temperature differential induced effect. You can see here this is a schematic showing if you are talking about a mass concrete. Imagine this is a cross section of a concrete column, and when the formwork is removed, the heat generated in this blue or the peripheral region is lost into the immediate environment, which is actually cold. Okay. So, but at the same time at the core of the concrete you will still have reasonably high amount of heat. So, there is a temperature difference or thermal differential temperature between the core and the peripheral region of the concrete, and because of this differential temperature you will end up in having the concrete will experience significant cracking near the peripheral region. All these black, this indicates the cracked region. So, the cracking might happen at the peripheral region, and imagine now a case if you have cracking and if you have reinforcement near the cover concrete, you will also have corrosion related problems, might have corrosion related problems at a later stage. So, you do not want the concrete to crack. So, how do you ensure that this does not happen is making sure that the heat generated inside is not lost into the atmosphere. So, you have to maintain a good formwork and a good insulation around the peripheral region. Something has to be covered, so the concrete has to be covered with a good blanket or some measures. So, which we will also talk later what are those measures. Now, talking about not that cold, but reasonably cold environment, which is like let us say when you talk about if the temperature is about 10 degrees Celsius, what happens to the setting time. You can see here setting time is almost increasing by almost twice. You can see final set there is a double 2 times increase in the setting time as you go from 23 degrees Celsius to 10 degrees Celsius. So, this is the 23 degrees Celsius data and this is the 10 degrees Celsius data, and it is a significant difference. So, you have to really consider various measures on how to ensure that the concrete is actually setting fast enough. So, this is one way by to achieve that is by using finely ground cement. Basically, the idea here in the graph you will see type 3 cement, which is the designation used in the US, and you have type 1 or 2 cement, which is the usual normal cement. So, you can see here the normal cement type 1 or 2, which is the square markers, and the triangular one which is type 3, which is the finely ground cement. So, you can definitely within 1 hour 1 day, that is 24 hours, you see a difference of about how much heat release, what is the difference in the heat release, about from 175 to about 250, that is about 75 joule per gram of cement. So, that much heat release difference is there when you talk about different type of cement itself. So, this that heat is very good or necessary for the hydration for the concrete to get cured better or in an accelerated manner. And also we can use high C3A and high C3S cement, which will actually help in making sure that there is more and more reactions especially in the early stages of curing or hydration. Now, this image here or graph shows how the use of this rapid hardening cement can help in increasing the strength gain in the early period. So, let us look at here about 3 to 5 days, and here also about 5 days. If you look at, you can see that there is about 10 MPa strength gain or increase in the strength when you compare from OPC to rapid hardening cement. So, definitely the type of cement which you use definitely matters, and the content, like if the cement has high C3A or C3S, and at the same time if it is finely ground, then definitely you can resolve some of the issues which happen at the early ages of curing. Okay, we also have accelerating admixtures. Until now we were talking about the cement or the mineral admixtures or even the cement, which and how selection of cement can help in reducing the setting time and gaining early strength. Now let us look at accelerating admixtures, which can help in reducing the setting time and increasing the strength gain, especially at the early age. And this accelerating admixtures, they also actually reduce the liquidus temperature, but not significantly reduce the liquidus temperature, or it reduces only by about 2 degrees Celsius. Let us see also what is this liquidus temperature. It is the minimum temperature at which all the components of a solution can be in liquid state, and that means below the liquidus temperature the mixture will or the concrete will be partially or entirely solid. So, we have to have some admixtures or some way by which we can ensure that the mixing water is available for reaction. I will come to that later, but before getting there, let us see this accelerating admixture. What are the three main category? They use calcium chloride and accelerators which contain calcium chloride, and also non-chloride accelerators. So, I would prefer to use this non-chloride accelerator. Probably we may have to avoid the use of calcium chloride and calcium chloride based accelerators, because that might eventually lead to corrosion, which is not a good idea. So, we will focus, or it is better to go for accelerators without any chlorides in them. Now, there are also another technology where the admixtures contain seeds, okay, seeds of CSH, which function like a nucleation point for further reaction to happen and a help in setting. So, what you see here is you will have the CSH seeds and then cement grain, and then you have water, and these are also the CSH and ettringite needles and etc. You will see the needle shaped structure you will see. So, here the picture on the left side is without the CSH seeds, and whereas here this is with CSH seed. Okay. Now, this will help in gaining the early strength and reaching this 3.5 MPa. Let me correct this, this is M capital PA. Okay. So, that 3.5 MPa strength criteria is achieved, especially for cold weather climates. This is very helpful, because these seeds provide the nucleation point for the cement hydration. That is the technology. Okay. And antifreeze admixture is another technology where the addition of these admixtures reduces the freezing point of the mixing water by about 10 degrees Celsius. Okay. From 0 it might go to -10. Okay. So, because of that reduction you have more water available for the hydration reaction, and you can see in this graph here, when you have a control case where there is no antifreeze admixtures, this graph here, and the red one with antifreeze, you can see there is a drop from 0 to about -10. So, that this 0 to -10. So, that is the reduction in the freezing point of the two systems without and with antifreeze admixtures. So, essentially what it means is, during the cold weather conditions or cold climatic conditions, you can have more time for construction also. That means we can pick a time, and even if the temperature is up to -10, you can still do concreting with this admixture. So, these are some of the examples of chemical family which are used, and people have done some studies on how economical is this methodology of using chemical admixtures for mixing concrete. People have seen that there can be about 30% savings instead of going for heating or other conventional methods of cold weather concreting. So, just use a chemical which will be added to the concrete and which can reduce the freezing point of the mixing water in concrete. So, that is the idea here. Now, how should concrete be protected until the specified strength of 3.5 MPa is attained? Until, the word here is until the 3.5 MPa is attained, that means very early stages in the concreting. First thing is we have to ensure that sufficient moisture is available, and how do we ensure? By preventing evaporation of moisture from concrete, because when you mix concrete based on your water cement ratio, you already have the amount of water which is required for the hydration. All what we need to do is preventing them from getting out of concrete, that is prevent evaporation. And then also we can use curing compounds to prevent the moisture loss from the surface. And one important thing to note here is when the temperature is in the freezing range, like less than 0 degrees Celsius, it is not recommended to use water curing, because that water which you use for curing will stay on the surface of the concrete, which eventually can freeze and which will lead to further damage to the concrete. So, water curing is not a recommended idea. So, main thing to do here is first protect your concrete structure with a plastic sheet or something like that, so that evaporation does not happen, and then another way is providing a membrane, which is basically the water curing curing compound. Now, how should concrete be protected after the specified strength is attained? That is slightly not in the very early stage, but after that. How do we ensure? Mainly by ensuring that sufficient heat is available, or the heat which is coming from the concrete is not lost into the environment, and also you can provide external heating to the concrete. In this slide we are talking about external heating, which is direct heating of concrete should not be allowed. Directly we should not. So, as you see in the picture on the top right, you can see that there is a flame and then there is a enclosure on top of the concrete surface, which provides a hot air around the uniformly on the concrete surface. So, the uniform heating is essential, not direct heating or a localized heating, and maintain at least 40% relative humidity inside the enclosure, because if you keep it too dry, then concrete will dry and it will not have enough moisture for hydration to happen, especially near the surface. The other way is by keeping the environment hot or providing external heat by using hydronic heaters or these heat transfer hoses which you see, and also by providing a blanket. So, two ways: one is the heat which is generated from the concrete has to be contained, and other is you can provide an external or the immediate surface of the concrete, whether it is air or the ground below, has to be maintained at a reasonably higher temperature, so that the concrete heat from the concrete is not lost into the environment. And this here are some key features which you can read later on, looking at what are the qualities to look for when you talk about these concrete blankets or insulation blankets. So, good quality concrete is possible. This picture very clearly shows that. You can see that all around the concrete slab which is being constructed, you have snow capped region, trees, and the job site but is very clear. There is no snow on the concrete surface, and then concrete is well protected, or in this picture that's plastic sheet which you see around, and also the blanket, it is going to keep the concrete well protected from losing the heat which is generated because of the exothermic reactions, and at the same time the the immediate environment immediate environment of the concrete can be maintained at a reasonably high temperature. So, if we do all this and proper planning and arrangement for protecting. So, the protecting concrete is also very important. It is not only the materials which you put like the finely ground cement or a cement with high C3S or C3A, and chemical admixtures like antifreeze freezing chemical or accelerating admixtures. All that is fine in when you talk about the material aspect. Then you have to place the concrete properly and make sure that the initial stage you have sufficient moisture available as water, preventing frost attack, and then make sure that the 3.5 MPa strength is gained, and then protect the concrete by preventing the moisture loss, further moisture loss, and also heat loss. So, if you do all these things, I think we can really have good quality concrete like we see in normal climatic conditions. Now, freeze-thaw attack, if we talk about later ages, it happens. So, when the temperature of concrete is below 0, the hardened concrete temperature, I would say here hardened concrete is below 0, the water does not all freeze immediately. So, the freezing point it also depends on at time depends on the size of the pores. Okay. So, water in the smaller pores need less than 0 degree temperature to freeze. Example, if you are talking about water in 10 nanometer pores, it will not freeze until -5 degrees Celsius. If you are talking about 3.5 nanometer pore, it will not freeze until 20 degrees Celsius, and if it is gel water, will not freeze until -78, that is much more small pores. So, you can see this. So, at the same temperature, what it means is there could be some water which is already frozen and some which is not frozen, depending on the size of the pore where the water is staying or occupying. And as the water freezes, it dilates and or expands and compresses the remaining water in the same pore. So, that is something which happens, and what happens is during this process of dilation, it pushes the water and that pressure is relieved if there is sufficient pathway available for that water to move into another pore or void, and if no voids are available in the near vicinity, then the pressure may build up, which eventually leads to cracking or rupturing of concrete. So, this is what I just mentioned. So, here you can see here a little bit of ice is formed here, that ice will push the water near there, and this water can actually flow into the void, and if that void space is nearby, you can see here water is flowing to this, and then a small ice is formed. The picture on the right end shows that how this ice is formed. This is one of the classical images from Berkeley, where they have captured this ice formation in inside the air void in cement paste. Very nice image. You can see a lot of ice formation happening, and so this is what really happens. So, if you have an air void, then it will not exert pressure, but if you do not have air void, then it will exert pressure and lead to cracking. Now, cyclic freeze-thaw exposure can also damage the concrete. This is first it is I am showing an example of what happens in the web. This is a picture from the internet, but I thought it is a very nice demonstration, so thought of using it. You can see here in a small crack in a rock, water collects, and after some time that water freezes and then pushes down. You can see it pushes down and it expands, and like a wedge it pushes in, and here that rock is now cracked into 2 pieces. You can see. So, something like this will happen depending on the number of cycles of freeze-thaw. So, for example, this number of cycle depending on the geographic location and climate, depending on the climatic condition, it could be daily cycle like diurnal variations, or weekly, monthly, or even annual, depending on where you are. The number of cycles is what matters here, not the duration of the frozen the freezing the time. So, it is a number of cycles which matters. So, number of freeze-thaw cycle, if it is more, then you will have more more and more damage induced into the concrete. Now, cyclic freeze-thaw exposure can also lead to popping out. You can see here. So, as we discussed, this ice will form inside the concrete, it will push the cementitious system and it will lead to cracking and popping out. As you can see on the picture on the left, it is a slight popping, it is about to pop, and then on the right side you can see that it is completely popped, and then you can very clearly see the same aggregate is also cracked. The so, the pressure is so much that it can also crack the aggregate. So, as you see here, this is the aggregate which cracked. Okay. So, the cyclic freeze-thaw exposure can also lead to something called decracking of concrete. Why this decracking name? It comes from based on the pattern of cracking on a jointed concrete pavement. You can see here picture on the right side, the sketch on the right side where which shows 4 slabs 1, 2, 3, 4, and the joint this shows like an alphabet D, and that is why it is called decracking, and which is observed visible here. If I draw something like this, you can see that decracking on this highway pavement. And so, the idea or what happens is freeze-thaw during the freeze-thaw exposure, the expansion of aggregate might happen, because depending if there is pores inside the aggregates, it might expand because of the ice formation inside, and also eventually that expansive forces will push the paste around, and which will lead to the failure of the paste. And then parallel cracks away from the saturation points. So, you can see these cracks, these are the parallel cracks which are actually happening. So, here also you can see parallel cracks, they are actually away from the joint, which is the saturation point. So, this decracking is something which is widely observed especially on this exterior concrete structure, exterior elements such as roads, which are directly exposed to the environment. Now, water saturation and cyclic freeze-thaw exposure can also cause internal cracking, especially in cases where the concrete is in direct contact with free water. So, because of the capillary suction, the internal concrete absorbs or sucks in all the water from the immediate environment, and when the temperature decreases, that water will become ice, not at the near surface, but water inside the concrete, leading to multiple micro cracking, or maybe in a larger crack also. Significant cracking you can see on this picture, both the images you can see, even the aggregates are also cracked. So, all this expansive behavior, the stress induced because of them is very high, which will lead to cracking of aggregate and eventually of the entire concrete system. Now, they can also, this kind of exposure can also lead to surface scaling near surface. You can see here picture on the left side, lot of material is lost at the near surface. So, this again because of the formation of ice, because of the absorption of water into the near surface concrete, and then with that ice formation it leads to cracking of the concrete at the near surface. And eventually, so this surface scaling will happen, and then eventually you will have multiple deterioration, because new surfaces get exposed, and then it leads to significant loss of the material, as you see in this picture on this at the center, and eventually the entire concrete cover can be lost due to this kind of freeze-thaw attack, and then once the entire cover is lost, then you will see the reinforcement getting exposed and corroded, which definitely affect the structural capacity of the system. So, how do we handle? The main approach is to use air entraining admixture, so that this freeze-thaw attack, so that you provide enough air voids space available in the concrete at which ice can form without exerting pressure onto the surrounding aggregates or the cement paste hardened concrete system. So, this picture also very clearly shows that if you increase the air content about let us say 5 to 6%, you have good quality concrete or durability factor is increased. Now, another damage mechanism or deterioration mechanism is alkali-silica reaction. So, ASR is the abbreviation, alkali-silica reaction, some people also call it AAR as is seen here, alkali aggregate reaction, but because most of the aggregates are silica rich, we can call it alkali-silica reaction. What it is? It is the chemical reaction which happens in the presence of moisture, okay, and this chemical reaction happens between the active mineral constituents and the alkali hydroxides, active mineral constituents and the alkali hydroxide present in concrete. So, we will see what happens when you have water, alkalis and reactive aggregates. This combination leads to alkali aggregate reaction or alkali-silica reaction. The picture on the bottom right shows an example how it looks like. You can see this all this blue colored blue color region that indicates the gel which we call ASR gel, and this gel induces significant pressure onto the concrete system, or it is expansive in nature, which leads to increase in the stresses, expansive stresses, and it can even crack the aggregate. You can see here an aggregate is cracked, this is also showing aggregate itself is cracked, and also significant cracking in the cement paste. So, the like we discussed in the sulphate attack, ASR also induces a lot of cracking of the concrete system or the entire matrix gets damaged. Now, let us look at why ASR occur in concrete structures. As we know, there is a lot of hydroxides of sodium and potassium present in cement, and that can react with the reactive aggregates, which are porous silica aggregates, especially when they are reactive in nature. They will react and form a gel that can absorb water. Okay. When it absorbs water, the volume increases and it induces expansive stresses onto the concrete. Now, this gel absorbs the water and it occupies all the available pores, and once all the pores are filled, then further expansion causes cracking. Okay. Means until the pores are filled, there is no stress induced onto the surrounding concrete, but once the pores are filled, then it starts inducing stress onto the surrounding concrete and leading to cracking. Now, once let us say there is a dry environment and then all this moisture gets evaporated, and then it leads to dehydration of the gel, and that will leave open cracks or voids in the system, and later on you can again have more moisture coming into the system, and then further reaction can happen, and this can lead to continued formation of more and more gel and leading to significant cracking. Now, when silica has high surface area and if the concentration of alkalis are low, then you will have some non-swelling gels, and which may not induce really significant damage. So, let us look at also which type of silica can be selected. So, in this table, as you see on the right side, it indicates if I use a particular type of silica, what is the expected life for that structure. So, as you go down on the table, you get better and better aggregates. Now, what is the reaction mechanism? So, the high pH in the cement paste promotes the hydrolysis of reactive silica, and you can see here hydrolysis of reactive silica, and it becomes SiOH bonds, and then this SiOH bond reacts with the paste to form SiO, and which further absorbs the or reacts with the sodium potassium and calcium to form a gel, and this is the gel which we are calling as ASR gel, which is expansive in nature, or sometimes it absorbs the moisture and expands. Now, how all this gel formation leads to what are the type of cracking which we observe, or how can we detect? So, this deleterious reaction is known for long time. In 1940s itself, people have identified this, published in 1940s. This picture you can see 1936, which is one of the first images showing ASR induced cracks. You can see it's map cracking, not a specific direction, and here also you can see vertical cracks on a column, because on the column you have reinforcement, and when there is a reduction in the strength of the concrete, the reinforcement will try to push the concrete, or in other words the crack is along along the stress path. So, that is something, but it is not straight line crack. If you look close up, you will see that there is a lot of map cracks on this column also. So, essentially what it is telling is the cracking is happening because of the stress generated from within the concrete system, and not because of the corrosion or any other mechanisms. So, you can see in this picture, on the left side you have a bridge column, and I have seen this bridge column. On the other side of this same bridge, you do not have any cracking, because it is the same concrete. On one side you have significant cracking, and on the other side you do not have any cracking. Main reason is on this side, with the side which is visible to you. Unfortunately, I do not have the other photograph of the other side, but you can see here there is significant cracking, and this is mainly because there was a drain pipe and it was giving water, providing sufficient moisture for that reaction to happen, for the ASR reactions to happen. So, as I showed earlier in this bottom left picture here, water is also a key factor. So, if you can keep the structure very dry, you may not see ASR induced reactions. So, there are other examples like a dam structure and concrete pavement, where also you can see significant map cracking. These are all due to ASR induced cracking. Or you can see the width, this is at least about an inch wide crack there, and these are additional examples showing how significant this cracking can be. So, on the left you can see a coin, and then fingers are inserted into the crack, and then also significantly wide crack on slab elements. And main point is all these cracks will lead to, or will help other deleterious elements to enter the concrete and eventually lead to corrosion of the reinforcement inside, which is a big problem later. Now, how do we test for assessing ASR? I am just showing multiple tests here. First thing is looking at the type of aggregate, or if there is any ASR gel present in the system. So, this is one test where a uranyl acetate is used. You spray this onto the concrete surface, and then you can look through and then see that gel fluorescence test for detecting ASR. So, in this picture you can see this is the aggregate region, and you can very clearly see that around the aggregate you have some different color, and that is all indicating the presence of ASR gel. And there are also other tests like mortar bar test and prism test, where mortar bar is mainly just to look at the cement paste system or even the mortar system, not the large aggregates presence. But there are also another test which is for concrete prisms. So, the picture on the bottom right side is just to show you how both these mortar bar or prism test is done. Basically, a prism is made, and then we look at the change in the length. If it is expanding, there will be increase in length of the specimen, and that will kind of tell you how severe could be ASR. I mean, how severe ASR type reactions can happen. Now, how, let us say you already kind of finished the construction of particular structure and then you find that there is ASR type problem, then how do we mitigate that? And so, I am going to show you multiple types by which people have tried impregnating the structure with lithium. That is the so far people say that is the best technology. And here the first one is by spraying lithium onto the concrete surface. These are concrete roads and this is a barrier, you can see there, and also vacuum impregnation is also applied. Here in the first one you spray it, and the second over here it is vacuum impregnation, where you create a vacuum pressure to suck the lithium solution into the concrete surface, but it is probably more expensive to do all this, it is not very easy. And also there are electrochemical methods where you apply a particular voltage which will drive the lithium ions into the concrete. But again, just look at here this particular project, for 2 concrete columns it took almost 8 weeks to complete, to impregnate sufficient lithium into the concrete. So, it is expensive, but sometimes you might end up in situations where it is very important and you cannot really look at money, but to protect the structure. Now, how this lithium treatment, what is the idea behind? So, if the lithium to the sodium plus potassium concentration, if it is greater than 7.74, then we say the expansion is minimum. So, this is the typical value used, the ratio requirement, how much lithium to be impregnated. So, typical dosage is about, let us say 4.6 liters of 30% lithium nitrite solution for every 1 kg of sodium oxide equivalent, okay, in concrete. So, the picture the graph here at the bottom left shows the difference between the expansion exhibited by a control system, that means no lithium treatment, and this is lithium treatment for 10 weeks and 16 weeks. So, point is you have significant reduction in the expansion from about 0.2 to less than 0.15%. I mean that is significant reduction, that is about 30% reduction in the expansion. And also if you have heavy cracking, moderate cracking or light cracking, the amount of lithium requirement is also apportioned accordingly. This is an example showing how this amount, the 4.6 liters per kg of per kg sodium oxide equivalent is come up with. So, you can go through this more detail later, and so I think that is it. For summarizing, we looked at both the cold weather concreting and associated issues and the ASR. So, in cold weather we were talking about can the cold weather can affect the properties of fresh and hardened concrete and finely ground cement and cement with high C3S or C3A content, and chemical admixtures, either an accelerator or an anti-freezing chemical can help in enhancing the setting time. And also I do not have it written here, but air entraining admixtures can also help. So, here air entrained concrete performs better than normal concrete, and this figure of 3.5 MPa strength. So, you should ensure that the concrete achieves 3.5 MPa strength, and then the further protection of that concrete is essential by ensuring that all the moisture is maintained, sufficient moisture level is maintained, and at the same time sufficient heat is maintained. Then concrete will continue to develop further strength. And the in terms of ASR, we saw that ASR is basically the reaction between alkali in the cement, alkali content in the cement, and the reactive aggregates, and different types of aggregate can have different levels of reactivity, and you have to probably choose low reactive aggregates, so that the such ASR related problems will not happen. And ASR can be identified based on the crack pattern, typically map cracking, and it can be controlled by lithium treatment. Also this is not very easy to do, it is very time intensive and expensive method. So, best way is, again like I mentioned in the last class, prevention is better than cure. So, if we can take care of good quality materials, if we can ensure that good quality materials are used, we can avoid ASR induced problems also. So, these are the references which were used for making this lecture notes. Thank you.